Inside the Machine, a documentary about the technology that makes data centers work. In the fraction of a second it takes to tap a button on your phone, a signal travels at the speed of light to a building you have probably never seen. Inside that building, thousands of computers wake up, locate your data, process it, and fire the answer back, all before you even notice. That building is a data center. And understanding how it works means understanding the invisible engine behind nearly everything digital in our lives. Every data center is built from 5 essential layers, stacked on top of each other. First, the IT equipment, the servers, storage drives, and network switches that actually process and store information. Second, the power infrastructure that ensures the building never goes dark. Third, the cooling systems that manage the enormous heat produced by computing hardware. Fourth, the networking layer that connects everything inside and out. And fifth, the software layer that makes physical hardware available as flexible, on-demand services. At the heart of every data center is the server, a powerful computer with no screen or keyboard, optimized to run continuously and handle thousands of simultaneous requests. Servers are stacked into metal frames called racks, each rack typically holding up to 42 servers about 2 inches thick. A large data center holds tens of thousands of racks, row upon row, stretching as far as the eye can see, all humming together, waiting for your next search, your next message, your next streaming request. For decades, data centers ran on CPUs, central processing units, which excel at running complex tasks one step at a time. But artificial intelligence changed everything. AI requires running millions of simple calculations simultaneously, and for that, you need GPUs. Graphics processing units were originally designed for video games but turned out to be perfectly suited for AI. Today, a single AI GPU chip like the NVIDIA Blackwell consumes over 1,000 watts of power, more than a microwave oven. And a rack full of them draws as much electricity as 50 average homes. What happens when the power grid fails? For a data center, the answer is nothing. Because data centers are engineered to never go dark. When grid power cuts out, battery-based UPS systems, uninterruptible power supplies, kick in within milliseconds, buying time while massive diesel generators spin up. The industry uses a standard called the tier system to measure reliability. Tier 4 data centers, the gold standard, have duplicate, fully independent power systems and achieve 995% uptime. That means less than 53 minutes of potential downtime in an entire year. Here is a problem that most people never think about. Computers are, essentially, very expensive heaters. Every calculation a chip performs produces heat as a byproduct. A modern AI GPU chip runs so hot that without active cooling, it would destroy itself within seconds. In a traditional data center, cold air is pumped through the floor and hot air is vented through the ceiling, a technique called hot aisle, cold aisle containment. This works for ordinary servers. But today's AI chips produce so much heat that air cooling alone is no longer sufficient. The data center cooling industry is undergoing a revolution. Traditional air cooling handles racks drawing up to about 15 kilowatts. A step up brings rear door heat exchangers, panels of cold water attached to the back of racks that absorb heat as it exits. Then comes direct-to-chip liquid cooling, where cold water or coolant flows through pipes directly pressed against the processor chips. This approach can handle racks drawing 120 kilowatts or more. In 2025, direct-to-chip cooling crossed a major milestone. Microsoft began deploying it across all of its Azure data centers worldwide. The most radical cooling approach takes things one step further: immersion cooling. In an immersion-cooled system, entire servers are submerged in a tank of special non-conductive fluid, similar in appearance to mineral oil. The fluid absorbs heat directly from the chips, with no air involved at all. In two-phase immersion, the fluid actually boils at low temperatures, turning to vapor as it absorbs heat, then recondensing and dripping back down a completely closed, self-sustaining loop. Immersion-cooled racks can handle densities of 100 to 250 kilowatts, making them the only viable option for the most extreme AI workloads. Inside a data center, data moves at extraordinary speeds. The backbone is fiber-optic cable, thin strands of glass that carry pulses of light rather than electrical signals, enabling data to travel at the speed of light with minimal loss over long distances. As recently as 2010, data center networks operated at 10 gigabits per second. Today, cutting-edge connections run at 800 gigabits per second and 1.6 terabit connections are entering production right now. Within 5 years, most AI data center network connections are expected to be fully optical, replacing copper with light throughout the entire facility. Now let's look at the software layer, because the physical hardware is only half the story. Virtualization is the technology that allows one physical server to behave as if it were many separate computers simultaneously. Software called a hypervisor divides the server's resources and creates multiple independent virtual machines, each running its own operating system and applications. Containers take this further. They are lightweight packages that bundle a single application with everything it needs to run, making software fast to deploy, easy to scale, and simple to move between machines. Container orchestration platforms like Kubernetes manage thousands of containers automatically across entire data centers. The arrival of large-scale artificial intelligence has fundamentally changed what a data center needs to do. An AI data center is not simply a normal data center with more servers. It is purpose-built as one giant, interconnected supercomputer with hundreds of thousands of GPUs linked by ultra-fast fiber, all working in tight coordination as a single machine. Training a large AI model requires millions of calculations running in parallel, across thousands of GPUs, 4 weeks at a time. Every GPU must communicate with every other GPU at incredible speed, which is why AI clusters require 16 times more fiber cabling than traditional cloud racks. AI is not just a workload that runs on data centers. It is actively redesigning what data centers are. How do you measure how efficiently a data center is using its energy? The industry uses a metric called PUE, power usage effectiveness. It is calculated simply, total facility energy divided by IT equipment energy. A perfect score of 1.0 would mean every single watt drawn by the building goes directly into useful computing. In practice, the industry average is around 1.54, meaning 54 cents of every dollar spent on power goes to overhead like cooling and lighting. The best hyperscale operators do far better. Google reported a fleet-wide PUE of just 1.09 in 2025, in part by using its own AI systems to optimize cooling, reducing cooling energy requirements by roughly 30%. The technology inside data centers is evolving faster than at any point in history. Silicon photonics is replacing copper electrical connections with light-based optical connections, cutting power consumption by 3.5 times while boosting speed. Nuclear power, specifically small modular reactors, is emerging as the only energy source capable of delivering the consistent, around-the-clock power that AI workloads demand. And the data center itself is beginning to shrink, with smaller edge data centers being deployed closer to cities and users, reducing latency for real-time AI applications like autonomous vehicles, smart cities, and instant medical diagnostics. Inside every data center, millions of carefully engineered decisions converge: the right chip for the right job, the right cooling for the right heat, the right network for the right speed, and the right software to make it all usable from anywhere on Earth. They are not glamorous. They have no windows. They are surrounded by fences and cameras and silence. But they are the reason the modern world works. Every message you send, every file you store, every AI that answers your questions, it all lives inside these extraordinary machines. And they are getting more powerful, more efficient, and more essential every single day.